Hi, I'm Mrs McTaggart, and in this video we're going to be looking at the topic of similar shapes, often sometimes referred to as similarity as well. And this is the first lesson in a series of 4 videos, and we're going to be looking at length scale factor here. So two shapes are said to be what's called mathematically similar if one is an exact enlargement or reduction of the other. So what I've got is another example here of 2 rectangles. Now I have drawn these that they are mathematically similar. The smaller one is a complete reduction of the bigger one. And if you look at the dimensions, we can kind of try to explain why that is. If you look at the length and breadth of the first rectangle, can you spot what number I can divide these numbers by to get the smaller numbers? Or in reverse, if you look at the small to the big one, can you see the connection between the numbers? The smaller one is exactly each of these numbers divided by 3. 6 divided by 3 is 2. 3 divided by 3 is 1. So this shape is said to have what's called a reduction scale factor of 1/3. It is 1/3 smaller than the other one. And it is a reduction scale factor of 1/3 because technically we are dividing the lengths by 3. But our scale factor generally is what we're going to multiply by. So if I multiplied each of the length and breadth of the big rectangle by 1/3, I would get the smaller rectangle lengths. Let's have a look at another one. So this time I have a square going to a bigger square. If you look at the connection with the sides, I have multiplied the sides by 4. So this shape is said to have an enlargement scale factor of 4 because I'm multiplying the lengths by 4. Okay. One thing that it should have said up the top of this slide is that these squares are mathematically similar. But in fact, all squares are mathematically similar, so I didn't necessarily need to write it that time. So we've talked about mathematically similar shapes. These 3 rectangles, only 2 of them are mathematically similar. So if we have a look at dimensions, which ones is it? Well, if I go from the yellow to the blue, double 6 is 12. But double 4 is not 9. So those 2 are not similar to each other. So we'll now try comparing the yellow one to the pink one. The connection isn't quite double here, but I have noticed if I multiply 4 times 2.5, that will give me 10. And 6 times 2.5 would also be 10. So this one does have similarity. So these are the mathematically similar shapes. And just to check, there is no similarity between the pink and the blue. There is no way to get from 10 to 9 or 15 to 12 or vice versa. So they are the mathematically similar ones. So what I've done is I've just taken the 2 rectangles from the first slide again to explain why they're not mathematically similar. At first glance you could think they are because 6 times 2 is 12. But whatever you do to one side, you have to do the same to the other, otherwise it's not mathematically similar. So if I was to do 4 times 2, that would be 8. So if that 9 had been an 8, they would be mathematically similar. But they are not similar because 4 times 2 does not equal 9. And a does not equal sign in maths is an equals with a line through it. So we have not multiplied both sides by the same thing here. So not mathematically similar. Again, here's another pair which is the mathematically similar ones here. Let's look at the red to purple for a quick instance. It looks like 25 doubled would give me 50. So 10 doubled, well, I would be expecting that one to be 20. So they're not the mathematically similar pair there. Let's look at the green to the purple. Well, 4 times 4 would give me 16. But 10 times 4 I'd expect that one to be 40. So that's not the mathematically similar pair. So the last option is look at the green to the red. And it's got that same scale factor that I used before. Bad examples by me. 4 times 2.5 gives me 10, and 10 times 2.5 gives me 20. So these are the mathematically similar ones. So let's go down to action and do some actual questions. So you've heard me talking about this thing called the scale factor a couple of times. The scale factor in maths is in definition is what we are multiplying by to get the missing length in our new shape. Now your scale factor can either be a whole number, it can be a top heavy fraction, or it can just be a simple fraction. So you have 2 things to consider. Is the new shape you're finding the missing side in, is it an enlargement or is it a reduction? So if it's an enlargement, it will always be big over small you'll be using. And what I mean by these is we compare the sides. Sometimes it's really obvious that I'm just doubling or trebling. But when it comes to ones like previously where I had the 4 and the 10, it wasn't so obvious. So for that one from the 4 going to the 10, I would say, oh, well, that had an enlargement scale factor of 10 over 4, which became 5 over 2. And you'll notice that enlargement, you're always times by something bigger than 1. But if I was going from a reduction and I was going from the 10 to the 4, I would put the small number on top and I'd do 4 over 10, which would simplify to 2/5. And if it's a reduction, you will always be multiplying by something less than 1. So let's see this in action. Now, I've used the terms big and small. Some teachers use new and old, and we always talk about our original shape and our new shape. So here is an example. These shapes are mathematically similar. We always have to tell you this in a question, and if you look out for that, it's a good clue that it's this style of question. So if they're mathematically similar, the first thing you have to do is get the scale factor. And I've prompted you into this, but we don't prompt you in it in the exam. So scale factor is the connection between the two corresponding sides. So I've got a 3 and an 8 there, and it's pretty obvious 3 times 6 is 8. So in this one, my scale factor is simply a whole number of 6. So the missing side, x, is simply 6 times 5, which is 30 centimetres. Now let's look at this. We're not prompting you into the 2 bits. So again, these two shapes are mathematically similar. We're looking for x. Now this time, x is a reduction. So my reduction scale factor, I can't be bothered writing that, so I'm going to write RSF for short. Now it would be the small lengths, you match up these two lengths, and if you're going for a reduction, remember you do small over big. So 4 over 20, and if you simplify that down, that is a 1/5. Now you might be able to just look at that and go, 20 divided by 5 is 4, and divided by 5 in maths is written as times by a 1/5. So your scale factor is a 1/5, the second shape is a 1/5 of the original one in length. So my missing side x is simply 1/5 times the length that corresponds with it in the other shape, which is 1/5 of 15, which is 3 centimetres. So my new length would be 3 centimetres. Okay, question 3 again. These are mathematically similar. We've gone for a reduction again. So this time we have a reduction scale factor. And it's not as obvious. There isn't a clear connection from going from 20 to 8. So we'll do small over big. So we'll do 8 over 20, which simplifies down using your 4 times table to be 2 over 5. So the second shape is 2/5 in length of the original one. So the missing side x will be 2/5 times the number that corresponds with another shape, albeit it's on the opposite side, but we know that the opposite sides of an arrow match. So it would be 2/5 times 30, which is, remember, good old divide by the bottom times the top. 30 divided by 5 is 6, 6 times 2 is 12. So the missing length in this one would be 12 centimetres. So if you want to practice some of these, here's a couple more to do. Remember that if you're doing enlargement, it will be big over small. So for the first one here, you would do 60 over 20 for your scale factor. Simplify it and times by the missing side. Okay, and then if you unpause the video, you can check your answers there. Thanks very much for watching. Bye-bye.